Right.
Okay, good to go.
Yep. Sorry about that.
Okay. Hi everyone. Thank you for coming. My name is Callum McPherson. This is my colleague Vanya. We both work for Quantinuum. We're going to introduce you to, I guess, our software platform that you're going to be using for the hackathon starting tomorrow. I was fortunate enough to mentor at the last iQuHACK 2023, so I'm really looking forward to getting started uh, with the hackathon. Right. So just to give you a very brief one slide overview of who we are and what we do. So Quantinuum is, I guess, a full stack quantum computing company. We were formed at the end of 2021. There's a merger between Cambridge Quantum Computing and Honeywell Quantum Solutions. So we do a mixture of things. I think most of what we do can be captured under these three headings. So we work on a lot of quantum software. We're going to be introducing you to Ticket and Nexus in this presentation, which we'll be using for the hackathon. So Ticket is our software development kit and our compiler, and Nexus is our cloud platform that allows you to submit jobs to quantum computers and run them and organize your experiments. So we also do a lot of theory research. So we do chemistry, many-body physics, quantum error correction, QNLP, and quantum cryptography and other things. Last year, we launched the H2 trapped ion device. This has this kind of nice racetrack layout of qubits. It's got 32 qubits, it has all-to-all qubit connectivity, and we have like these high-fidelity 2-qubit gates, which is a very important metric. So now that I've introduced you to who we are and what we do, I'm going to get stuck in. So let's start with Ticket. So what is Ticket? So it's a quantum software library developed by us at Quantinuum. It's got a sort of Python front end that lets you build circuits and run them on real quantum computers and simulators. The core of Ticket is like this high-performance quantum compiler written in C++. We're solving a lot of complicated problems. So it's important that it's written in high performance code. We're fully open source, so you can visit our GitHub repository. We're open to contributions and collaborations. Central to Ticket's design, I guess, is this principle of being hardware agnostic. So the software doesn't get in your way. If you want to try out superconducting devices or ion trap devices, we support running circuits on all of these. Another benefit is it works nicely with other quantum software libraries that are out there, which I'm sure some of you are familiar with. So we have extension modules to interface with Qiskit and Cirq, Bracket, PennyLane, and several more. So you can easily install Ticket and get started by just running pip install pyticket. And yeah, that just installs the Python bindings and you can get started. I'll show you a tutorial run through in a sec. So let me just explain, I guess, the architecture of Ticket. So as I mentioned, we have this sort of core sort of C++ library, which is a compiler. Then we have the sort of Python wrapper around it. This allows sort of a user-friendly interface for sort of building and running circuits. And we have all of these different extension modules here that allow us to interact with different software libraries and also target devices from different hardware providers. So if you're used to writing code in Qiskit, you can quite easily convert your Qiskit circuit to a pyticket circuit and then submit it to any device you like. So yeah, so that to emphasize like code portability and using different backends to run your experiments. So let's look at a real quantum device here. So if you go to the IBM cloud platform and take a look at the available devices, you might see a diagram a bit like this. This is like a connectivity graph of a superconducting device. This is IBM Cairo. You can see like the qubits are laid out in this kind of topology. And an important restriction on superconducting devices is that they only allow 2-qubit gates between physically adjacent qubits. So if I wanted to do like a 2-qubit gate between a CNOT gate between qubit 10 and qubit 15, I'll need to do a swap gate to make that interaction possible. So this is like a important thing to keep track of. If you're compiling a quantum algorithm, you need to add a large overhead of additional swap gates that can really increase the complexity of your circuit and degrade the results. So let's show an example of compiling a quantum circuit. Here I've got a circuit for the quantum Fourier transform, which is an important subroutine in many quantum algorithms. I'm sure some of you are familiar with this. So if you look at this circuit diagram here, you can see that I have all possible pairs of interactions between qubits. So qubit 1 is interacting with qubit 0, 2, 0, and so on. So you could say I have like a complete connectivity graph for all of my qubits are talking to one another. And now if I compare this with this architecture graph here of the target device, you can see that it's much sparser and only allows interactions between neighbors in the device. So I have to compile the circuit to be a valid circuit to respect the constraints of the hardware before I can actually run an experiment or device. And there are other important restrictions like the gate set. So I need to convert these controlled unitaries into this gate set. And I want to do this well. I don't want to introduce too many additional gates because these additional gates all just increase the error that accumulates over the course of your computation. So now I'm once I have this circuit, I can then compile my circuit to look something like this. So you see now that I'm in the IBM native gate set, and I've all of the qubits are each assigned to the physical node of the device. You can see the circuit's quite a bit bigger. So like solving for these constraints typically involves adding a lot of extra gates. So I've added all of these swap gates, and this is a circuit that actually runs in the device. So it's important to do a good job of this if we want to run our circuits without too much error accumulating. Here's another example. Say I want to do this Toffoli gate here, this CCX. So it looks like this. And I can use Ticket to compile this down. Here I'm targeting our own sort of hardware, our own ion trap hardware. So I just create a circuit with 3 qubits and then add my gate. And then I can just compile the circuit by calling this get compiled circuit method on the backend class. And then I get a circuit which satisfies the constraints of my hardware. So it's in this ZZ phased X gate set here. Before I continue onto my code demo, do you have any questions so far? All good? Okay. What am I doing for time? Okay. Not too bad. So I'm going to run you through a basic example of building circuits and compiling them and running basic experiments. So let's start here with just a simple circuit that prepares a Bell state. So I can create such a circuit with just a single Hadamard and a CX gate. So I can create an instance of the circuit class, give it a name, say Bell in this case, and then just append this Hadamard and then CX gate. So we got a similar sort of API to other tools you might be used to. We've got this nice circuit renderer, which has this dark mode, but you can toggle these options, which is quite nice. So I don't know if you're familiar with the ZX calculus, but you can also take this alternate point of view in our circuit renderer. You can adjust things. It's quite useful for visualizing your circuits. So let's say I want, now that I've made this circuit, I want to run a very basic simulation to make sure this circuit is doing what I want. So I can import this AR state backend class, which is a very simple state vector simulator. It uses Qiskit's AR backend. So I can just run this, and you can see I get this state vector, and the amplitudes are exactly what I would expect if I had a Bell state. So let's do now a shots-based simulation. So we're just, all that's changing here is we're measuring our qubits and using the shots-based AR backend. So we're now running this circuit, this Bell state circuit for 1,000 shots, and then collecting statistics about our measurement results. So you can see we've got an approximately 50-50 distribution in the 1, 1, and 0, 0 states, which is exactly what you'd expect. You're essentially just flipping a coin every time. So draw a graph like this. So that circuit's pretty trivial. How do I build, say, more complex circuits? So I can, if I want to create a quantum Fourier transform circuit with 3 qubits, I can do it as follows. So I'm just adding this Hadamard gate and these controlled unitaries. You can see I just build up my circuit step by step, end up with something like this. Another thing you might want to do is create like higher level sort of subroutines to add as blocks in your quantum algorithms. So quantum Fourier transform is a good example. It occurs as a subroutine in phase estimation and other quantum algorithms you may have seen. So let's say I create another circuit, like this oracle circuit here, and I want to wrap this up in a box and then add it as a subroutine in a larger algorithm. I can do that pretty easily. I can use this circbox class, and I pass in my circuit, and then I can easily append it onto another circuit here. So I'm preparing this initial superposition, and I've added this sort of boxed subroutine. So this allows you to sort of compose quantum algorithms of like their building blocks, which is quite nice. Another useful thing you might want to do is just generate a circuit that implements a particular unitary transformation. You can do this for any unitary you like, up to 3 qubits. It's actually quite a mathematically involved problem. So say I have this unitary matrix here. I want to generate a circuit for it. I can just pass this into this unitary 2-qubit box, and it will automatically generate a circuit for me, which is nice. I'm just passing it like a NumPy array with this unitary matrix here. So I end up with this box like this. And this box can be easily decomposed, so I can see the sort of primitive gates underneath. Yeah, so this circuit just implements this unitary transformation here. It also very easily generates circuits from QASM. So QASM is like a quantum assembly language that's quite widely used. So if you have QASM files lying around, the natural thing you might want to do is sort of import or export to and from QASM. So it's very easy to do. It's just a simple QASM parser, and you can, yeah, here I've just got a phase estimation circuit, which I have lying around as a QASM file, and I can just generate a circuit like this. Last thing I'll show is just the sort of useful sort of code portability between Ticket and Qiskit and several other tools. So I defined this QFT circuit further up, but I can very easily just port this to a Qiskit circuit by just using this Ticket to Qiskit function, which is pretty nice. It means you don't have to rewrite your code every time if you're switching between different libraries. Okay. Just going to show you another quick example, and I'll hand over to Vanya. Yeah, so I'm going to talk a bit about running actual simulations and sort of analyzing some results. So let's say I have this phase estimation circuit. I've used a slightly bigger one in this case, just because it makes a few things slightly clearer. And now I want to run this circuit on an IBM simulator and sort of analyze the results. So I can use this IBM Q emulator backend, and this uses a noise model that emulates the real IBM device. So I'm just running this simulation here. And you can see as before, if I visualize the sort of connectivity of my circuit, I have all of my qubits sort of interacting with one another. So I need to sort of compile the circuit down and meet this sort of nearest neighbor connectivity constraint before I can actually run this circuit on my device. Yeah, you can see if I can, this is how the qubits are actually laid out in the device. This is a bit crammed here, but yeah, you can see this is much sparser. So here I can use this handy get compiled circuit method and just pass in my circuit and specify an optimization level. It's optimization level 2 by default, but I'll set it to 0 just for illustration purposes. This just does the bare minimum to get you a circuit that will actually run on your device. So you can see that now I've compiled my phase estimation circuit. It's quite big. And if you think about each of these gates, and in this context, will have some error rate. So you can see the more gates I have, the more error is accumulating and the worse my results are. So you can see I have 127 two-qubit gates here. Two-qubit gates are generally much noisier than single-qubit gates. So they're a natural metric you might want to minimize in the context of circuit optimization. And now if I look at the connectivity graph of my compiled circuit, you can see that I now only have these neighboring nodes interacting with one another. So now I'm going to run this circuit for 1,000 shots, just for illustration purposes. And you can see I get a graph that looks something like this. And those of you who are familiar with phase estimation will probably know that our phase, which we're trying to estimate, is encoded in these sort of measured bit strings here. Just so happens for this case that the correct answer is 0, 1, 1, 0, 1. So 309 of my 1,000 shots are landing in this basis state, which gives me my correct answer. So this is okay, but maybe we can do better by working harder at circuit optimization. So I can do the same as before, but just pass in this optimization level 2 argument. So this just means Ticket will work harder to optimize circuit. So we'll sort of traverse the circuit looking for sort of local redundancies and resynthesizing blocks of your circuit to try and reduce the two-qubit gate count. You can see that we've gone from 127 two-qubit gates to only 57. So if I look at the graph, I can see that a much larger proportion of my 1,000 shots are landing in this correct answer basis state, if you like. So seems that our better circuit optimization is indeed helping our algorithm find the right answer. So I should say that yeah, this is just to demonstrate that a lower gate count can improve your success rate with your quantum algorithm. This is not a particularly realistic experiment, but hopefully at least illustrates that. Did have more material, but I think it's a good time to hand over to Vanya.
Thank you very much, Callum. If you managed to guess which rainy European island he's from, I'm from the other one. And I'm going to talk to you briefly about Quantinuum Nexus. What's this? That doesn't look good to me. I don't know what you think, but from current slide, let's try that.
Yeah.
Oh, spinner, that's good. Promising.
Doesn't seem to like your slides.
No, it doesn't like them at all. Okay. Well, tell you what, okay, we won't do slideshow. Okay.
Just do it like this.
Yeah, this is fine. So I work for Quantinuum Nexus. Callum gave you a broad overview of the various software projects going on in Quantinuum, the research avenues we explore, maybe a bit of a discussion of the trapped ion quantum computers that we make. I work for a software engineer for Quantinuum Nexus. It's a web platform for using quantum computers. I will probably at some point in the talk call it Nexus. The legal team have reminded me I'm not meant to do this. I have to call it Quantinuum Nexus to distinguish us, I presume, from the brand of androids in the movie Blade Runner. So if you hear me use the word Nexus, yell at me, or more importantly, just don't tell the legal or marketing team at Quantinuum. So using quantum computers usually involves using the internet, and involves a lot of other things like storage, hosted compute. The quantum computers typically exist in faraway exotic places like Broomfield, Colorado, or Poughkeepsie, New York. Nexus aims to try and connect you and the quantum computers and try and manage a lot of your workflows, things that you do around quantum computers. Specifically, we try and look at areas that I'm going to try and break down in these slides, but process management, trying to manage your quantum algorithms. A lot of time, these might be hybrid classical quantum algorithms or using the ticket set of quantum compilation tools, running things on simulators. We also then try to focus a lot on collaboration tools. So the idea that you can share your results with colleagues, with team members for a hackathon. We also offer hosted compute. So for running simulations, for running compilation, for running your own custom algorithms at some point in the near future, hopefully, on our cloud software or our cloud infrastructure. We also aim to provide a standardized access to various quantum computers, including our own H-series devices, but also third-party devices. The idea being that you have a uniform API and interface to access these. And another thing we focus on is smarter storage. So the idea that you can hopefully store your circuits, your algorithms, your results, keep them there for many years, and then return and visit them at some point in the future. So specifically process management, a lot of the time, if you're working on a pretty complex kind of quantum workflow, it'll involve some classical steps, some quantum steps. We break these down into jobs in Nexus currently, although soon in the future we'll be able to offer more kind of complex graphical approaches to quantum algorithm management. Once you send off your job, the idea is that Nexus will take care of it, look after it, and handle any kind of ephemeral errors like network errors, and importantly, retrieve everything when it's ready. So for instance, if you're submitting a circuit to run on a quantum computer, Nexus would store the circuit, would store the result when it's ready, and would store a snapshot of the machine, so you have information on the error parameters associated with the machine, which might be important when you're trying to understand why it's so noisy. Also, if you compile a Nexus, you can see the intermediate compilation steps and see exactly what ticket did to the circuit in order to compile it. We also, focus a lot on standardized access. So the idea being that you can hopefully just add your credentials to your device of choice, and you'll be able to see exactly all the devices you're able to access and access them using our standardized API. That includes hosted simulators that we run in the Nexus infrastructure. We focus a lot on collaboration tools as well. So you can use concepts called teams. We have role-based access control for all resources in the Nexus database. So you can share things with people, but perhaps not give them the ability to delete these resources. You can't trust everyone. We try and build a pretty smart database for storing things. So The idea being that often your results you'd like to revisit in the future, maybe look at them at some point years from now, and be able to navigate them reasonably well. So we're trying to build out features associated with like labeling your data, attaching properties, maybe experimental parameters if you're running like a variational quantum eigensolver type style algorithm where you want to store the parameters for your circuit each time you run it. And yeah, a lot of like hosted compute in general. So we offer a bunch of simulators, including IBM simulators, iQuHACKs, and of course our own simulators for our H-series devices. And we offer a hosted kind of Jupyter interface, which allows you to have all the software pre-installed. Don't have to worry too much about logging into Nexus or anything. And if you are doing our challenge for the hackathon, you'll be using that hopefully seamlessly to participate. So Nexus isn't beta, it's not a real product yet, or it is a real product, but it's we're going to try and release some point later in the year. So yeah, I hope you guys have a good time using it. If it breaks, I'll run away. But yeah, so don't tell anyone I was here because it is secretly, not officially out yet. I'm going to run through just a quick demo of like using Nexus now. Which hopefully should work better than the PowerPoint presentation. Okay. So yeah, when you participate in the hackathon challenge, you'll get access to Nexus. You'll log in, click through some terms and conditions, then you'll be here. You are able to see your currently running jobs down here, able to maybe look at our docs. Importantly, I suppose, you can see the backends you have access to. So these are hosted simulators. See, oh no, Callum hasn't added his, that's okay. Or is it okay? Yeah. Okay, I'll have to fix that. That's okay. Yeah, so you can add your credentials for Bracket, for IBMQ, access our simulators. We use a concept called projects to try and organize your stuff. So there's project. We're now going to just hop over to the Jupyter interface. So if you're familiar with like Jupyter Lab, pretty much the same thing. Comes with all the software pre-installed. And we are going to run this little thing. Okay. So I think we're actually going to make some small changes here because Callum hasn't added his Quantinuum. He hasn't activated his Quantinuum account. Despite being an employee of the company. No, this is a temporary account. So this is a fresh account. So I won't tell the boss. Okay. So we're going to use AR for this demo, which is okay. It's another simulator. So we're going to just, so yeah, sorry. We use this concept called a config. When you want to specify which backend you want to target, you instantiate a config class where you can provide maybe some like parameters for setting up the device, but also maybe some, administrative bureaucratic sort of stuff. Thankfully, the simulators don't require too much of that. The standardized interface, which we get from Ticket, is this backend class. So you pass in a configuration and the name of your project. We then use, oh yeah, sure, good idea actually. Okay, yeah, thank you, that's a good idea. Okay, so we're gonna use the Ticket set of tools for just constructing a circuit here. Nice, simple one. We're then gonna submit the circuit over to Nexus to run in a compilation job. So hop over to Nexus, go look at our project. You can see, oh, it's actually already completed. It's a small circuit. I'm giving it a kind of random name. So simple compilation job, but we can indeed see what Ticket has done to it. In this case, it's actually only done 2 compiler passes, decompose boxes. You can see the circuit there. Synthesize Ticket. And we can see it's completed. See the backend is targeting. We're going to submit the circuit for processing. Give it 1,000 shots, why not? Hop back over to Nexus. Look, yeah, it's also completed pretty quick. You can see the circuit that's submitted, see the result. So yeah, during the hackathon, if you're submitting for the hackathon, we're going to try and guide you through the documentation resources we provide we're going to recommend that you target our H series simulator first, and then maybe the emulator. The emulator is noisy. It's a lot truer to the actual machine. And if you're submitting really big circuits for this phase estimation problem, you might have to end up queuing longer than I had to queue just there, but hopefully not too long. One thing Nexus does is it'll scale up the simulator resources for what your kind of workload. Yeah. So yeah, that's pretty much it. I think giving you a brief overview of Nexus, and I hope that everything works out well for the hackathon challenge. Yeah, we're happy to answer any questions about anything Quantinuum related. Well, we'll try. Don't ask too much about the machine. But yeah, thanks very much. How many of you guys are doing the Quantinuum challenge? Have you decided what challenge you're doing yet? Or okay. Okay, cool. Challenge will be super easy. No, it's not that easy. You'll learn a bunch of cool stuff, so it'll be fun. And you get to use Quantinuum Nexus. Okay, cool. Well, yeah. Oh, sorry. Yeah, go ahead.
What are like the usable qubits on the Nexus right
now?
Can you tell us something?
Yeah, so sorry. Yeah, normally you would if you have Quantinuum hardware access, you can target the H series devices. H11 I think is 20 qubits. H21 is 32 qubits. Unfortunately for the challenge, so you might have heard in the talk earlier, trapped ion quantum computers are very slow. We don't have enough of them to cater for demand. So for this hackathon challenge, you'll be unfortunately limited to the simulator or the emulator. The actual hardware, hopefully we're about to offer for hackathon soon, but yeah, so if you're a paying customer, you can access those devices, but unfortunately for the hackathon, we aren't able to offer them. Yeah. That said, the emulator is very close. It's to the actual device, and is like hosted with the device. They were right next to each other physically, so and pretty much built by the same people. Sorry, any other questions?
I'm just curious. I have nothing to do with the challenge, but could you tell us a little bit more about the process of creating the emulator as a function of the noise in the virtual machine? Like, how do you model it?
I don't know much about the noise model, but I know it's supposed to capture a lot more of the noise. It also includes like ion transport and the time taken for cooling and things like that. So there's a lot of like low-level details that are included in the emulation itself. As to like the physics of the noise model, I don't know the details of that. But yeah, it's supposed to, it goes through our whole like compilation stack, and all of the timing and everything is the same as it would be in the real hardware.
So you could go to the Quantinuum page, and there is something about our devices. There's exactly like a specification sheet for the emulator, and it outlines all of the stuff the emulator can do with all the noise models that are implemented. It talks a little bit about it, right? So actually, the Quantinuum website, it does have a little bit of information on the specification sheet. But if you go on,
I think that is. I'll try and live.
the product sheet.
Is that in products and solutions?
Hardware, and you should go to the hardware system H1, for example.
Hmm.
H1, H1. And that should be the emulator.
Oh yeah, emulator sheet.
And then open that one, yeah, and it's all about the emulator, and it's very extensive. And you actually can play with the noise model. You can turn things on, change. It's not recommended that you do that, but for kind of exploration for your algorithm, what could be your noise factor? I can find it. Like you can play with that. It's very expensive.
Anyone else?
you can find those data sheets for all other devices as well here, including the actual hardware.
Just a general question about emulator. Is it available to like customers to use, or is it mostly used in-house?
It's used both in-house by our scientists and for customers. Again, it's we're trying to actually, one thing Nexus is hoping to do soon is offer multiple copies of the emulator. Right now, we only really have one copy running at a time, so people have to queue for the emulator as well, despite the fact it is essentially just classical software. Certainly has some hardware requirements, but yeah, no, our customers is very popular with customers. Yeah, it's oh, cool. Well, oh, sorry, yeah, go ahead.
Question there.
Computational linguistics.
Yeah.
Oh, Callum can tell you all about that.
I can send you something to read on it. I don't work in that field myself, but yeah, I can pass you on to. Yeah.
We work in the Cambridge office and the Oxford office. Sorry, Cambridge, UK. So it's funny for us to come here. The other Cambridge. It's funny being here and seeing the street signs and being like, well. In the Oxford office, they work on the quantum natural language processing stuff. But yeah, Callum and I can show you documentation. The packages I think are publicly
I have
available.
a tiny bit of experience with Lambec, but I wouldn't. Yeah, I would mostly direct you to people that I can put you in touch with.
For one of the hackathons we did, they were expecting Callum to know all about it, and I think yeah. That's why I'm making a joke. I'm putting on the spot. Yeah, I wish I could talk more about it. It is super interesting, pretty crazy. Oh, cool. If there's no other questions, I think we have to go across to that other big hall we were at earlier for the career thing.
Careers meeting, yeah.
Careers meeting.
Mhm.
Yeah. Anyway, thanks a lot. Sorry, I didn't ask. That's good. There's only 2 participants.